So hello, everybody. I'm very happy to be here today to present to you our work in our lab at NTU. It's a joint work with Tristan Guérin, Thomas Perrin, and Sayandip Saha. So it's on True Stable Net, a neural network designed for Torus FHE. So broadly speaking, in one sentence memory, we are going to see how we can design a neural network for Torus FHE. This is the main topic of this presentation. So please, if you have questions, put it in the chat. I will be very happy to answer it at the end of the talk. First of all, quick words. So I did my my bachelor and my master at University Paris-Saclay. I'm a PhD student in Thomas Perrin's labs since 2020, and my research focus mainly on cryptanalysis and deep learning and safety, actually. Okay, so let's get started. First, global general introduction, then the goal presentations. So since 2020, since 10 years now, deep neural networks have managed to have great success. So especially in image, so we can think of image classification, image segmentation, denoising. They have really managed to tackle a lot of problems that was very difficult before. Also about NLP and text, the same. So now text classification, summary, all this kind of tasks which used to be very difficult now are pretty easy to do. The same stands for reinforcement learning. So now we call it deep reinforcement learning because you can do reinforcement learning with functions that use deep neural networks. Again, this also managed to have great success in many domains. And more recently, like since now 1 year or 2 years, like regeneration of image and text are really wonderful. We can think about ChatGPT or DALL-E 2. They are very great neural networks with very great performances. So this, of course, is possible thanks to cloud computing, open source datasets, and the large community. But what about trust? So in 2023, we can highlight some challenges, especially on reliability and trustworthiness of deep neural networks. So I'm going to speak about 3 of them. There are many of them, but we can think about the first one is, of course, interpretability. And because of the complexity of this function, they have this black box property or phenomena that we struggle to explain how the neural networks learns and what it learns. The second point is formal verification, like you cannot prove, or actually it's very hard to prove some properties on neural networks, fairness, robustness. These 2 properties, for example, are very difficult to prove. And of course, privacy. In fact, in a cloud setting, when you deploy your model in a cloud, like you need to trust the cloud provider. And usually it is not really the case. So, of course, these 3 main points are critical points for industries like military, energy, finance, healthcare. These 3 points are really a no-go for these industries. And today we are going to focus mainly on privacy. So when you deploy your deep neural network in the cloud, the ultimate goal is that you protect your model from a recovery, like you don't want the client to have access to the model, and of course the user don't want his data to be shared with the cloud provider. So this paradigm of privacy between the 2 key players of DNN deployment in cloud, fully homomorphic encryption encryption solves this problem. It guarantees, especially, it guarantees the data user privacy. And this is very nice because now we started to have some strong law and drivers like the European Union with the GDPR, which tries to force the user privacy. So what are the limits of this kind of technology? Of course, for deployment at scale, it's mainly the price, I would say. So for example, I'm going to show you here the state of the art. If, let's say, one person or one company needs to deploy his model and to infer one image of CIFAR10 for 10K different clients. And of course, we want this inference to be done with FHE. So that means that he encrypts his data, he sends it to the cloud, and the user received the prediction of the model encrypted, and he decrypted it with his own key in local. So what is the price if you want to do that, not for one client, but for 10K clients? So here I show you 3 different models with 2 different techniques of homomorphic encryption. So the first one is CKKS, and 2 teams, 2 different methods of machine learning. One is ResNet, the other one is Lola. The first one is made by a Korean team. The second one is made by an American team. And actually, you can see that the cost is pretty important, like almost 20K for the ResNet with a pretty good accuracy, 38 minutes per client to answer, and especially the memory is pretty huge. So that memory makes the cost very high. Also, the same stands for Torus FHE, for fully homomorphic encryption. If you want to do it with general deep neural networks today, you can do it, but it will be pretty costly. So the accuracy is a bit lower, but the time is also pretty important. The memory is less important than for ResNet, but the time is much more important. So for example, Lola, the second one is maybe the best compromise up to date. The key angle of that presentation is we want to decrease that price, that cost. This is really what we target to, what we want to do. And we want to do that especially by decreasing the memory needed to infer one CIFAR10 image. So how to decrease the cost? I would say that there are 2 complementary strategies. The first one is, of course, you can enhance homomorphic encryption or fully homomorphic encryption technology for machine learning. This is, I suppose that this is what your community mainly do. Also, for example, companies like Zama, they try to do that. The other way, the other complementary way is like you try to enhance machine learning technology for FHE. And this is our approach today. This is what we try to do. So the goal is to design a neural network for Torus FHE. We managed to do that by designing a neural network based on truth table. So pretty simple question. Can we invent a deep neural network, deep convolutional neural network, DCNN, for Torus FHE technology? Yes, no, maybe. And if yes, can it scale? And what is definitely at the end of the day, what is the cost of a deployment of such a technology? So globally, in a very high, super high level way, this is how a deep neural network looks like. So you have 3 main blocks, one at the beginning, one at the end. The first one is what we can call a pre-processing layer. So a pre-processing layer, it's actually only filters on the image or over your inputs. Usually we can pretty easily interpret it, see how it works exactly, and so on. The final block is the block of classification. So you project your vectors of filters on your class size. Usually also this one, it's a linear regression. It's a linear layer. It can be a MLP, but in our case, it will be a linear layer. In between, you have CNN layer blocks. So this in between, you have multiple layers of CNN. So for example, layer 1 to layer n. And in each of them, you have what we call filters. So CNN filters. Usually, you have between 32 to, I would say, 500 filters, generally depending on the layers that you're looking at. The goal here is to transform each CNN filter into a truth table. Okay? So this point is pretty important. The goal here is to transform each filters into a truth table. The preprocessing layer, we can handle it. The linear layer, we can handle it, but really the trickiest part in deep neural networks is these CNN layers that can be, there are multiple of them, and especially what are super costly to compute are these filters. So we want to transform them into a truth table. Okay, so let's go back to our question. Can we invent a DCNN for Torus FHE? Yes, but we need to do some compromise. So first of all, the preprocessing layer, we decided to do it at client side. So especially for CIFAR10, for MNIST, for other type of dataset, for smaller size of datasets, we don't really need the client side. But for CIFAR10, we need the preprocessing layer to be done at the client side, especially to handle the floating points. The last linear classification layer, if we can encode it in 4-bit or 3-bit or 2-bit or even 1-bit, well, we can handle it. And in between, we want interconnected truth table. Because if we have interconnected truth table, then that means that we have, sorry, I didn't introduce LTT, sorry, my bad. LTT here, LTTs are learning truth table. So this is the key component that we are going to see. They are exactly equivalent to lookup tables. Therefore, if we manage to do that, it's 100% compatible with Torus FHE ZAMA technology. And we can integrate our deep neural network with ZAMA technology in a very efficient way. Okay, so we are going to go in details on how we can do that right now. So if you have any question, again, maybe I'm just going to check quickly if you have any question, because this part was pretty important. Well, I cannot have access to the chat.
There is one question at the moment. It was, why does 38 minutes of CKKS computation cost $19,000?
Say it again. Sorry.
The question that was presented so far was, why does 38 minutes of CKKS computation cost 19K?
Because, okay, so if you consider that you have 10K clients, that means that you need, for each client, you need to rent a computer of 500 gigabytes RAM, because each computation requires 300 gigabytes of RAM, actually more than that, almost 400 gigabytes of RAM. So you need to rent 10K computers for 1 hour.
Okay, thank you.
Okay, So let's dive into how we can construct that truth table net. So key features. So our learning truth table block, which is exactly the CNN features, need to be exactly equivalent to an enumerable Boolean function. The complete distribution need to be computable in 2 power n operation, with typically n lower than 6, independently of the architecture. It needs to be designed based on neural networks, especially for easy training, especially easy compatible with PyTorch or TensorFlow or your favorite machine learning framework. It needs to be scalable and accurate when we apply it to large datasets, and actually that too. So for that, there's 2 main rules, actually 3 main rules. The first one is your inputs/outputs needs to be binary. In fact, if you want a Boolean function, you need your inputs and outputs to be binary. And each LTT input size needs to be small. Small means here lower than 6. Scalable and accurate. So if you want to manage to do that, you need non-linearity between the step function. So this one is maybe a bit more technical, but actually you need to think that, okay, you have a small function, but you want also like a small function because it takes small size input, but you want, like you're in deep learning, so you want multiple layers in that small function. That's all. You want not a linear function, you want the biggest non-linear function that you can have. Okay, so let's start by the basics, and then we will construct the learning truth table and TTnet truth table net step by step. So here, this is a classic perceptron. So you have n inputs and the bias here, and you sum all of them, and you have your activation function at the end. Of course, the inputs can be floating points, especially for images. First of all, you need to convert this Boolean, this function. Sorry, you need to transform this function into a meta function. So you englobe, you take all this white plus the activation function, and this become your LTT block. This become your truth table. Especially also you have n binary inputs. So normally everybody should be agreed that in 2 power n operation, you should be able to compute the complete distribution of that function. The question is how you can make this n low enough actually. So typically for, let's say for CIFAR10, n is equals, if you manage to transform it into binary inputs, n typically is 32 times 32 times 3. Okay, so this is actually 32 times 32 times 3 is too big, and we want n lower than 6. So how to do that? We need to focus on CNN filters first. Why? Because if I tell you that I can transform all the function in the world like this, I will be a liar. I need to reduce m. And for that, well, CNN is the perfect tool, because CNN is by design a type of function that takes a small size input. So typically, typically CNN features has by design small size input. C'est pas vrai. Normally, I don't know why, but normally I have an animation here. Copy link address. Okay, perfect. Okay, so for those who have never seen a convolution before, it can happen. So typically, this is one image. I don't know if you can see my screen. This is one image. This is the weights of that image for one CNN feature. This is the weights for one CNN filter, and this is the step function. So all these functions here can be considered as a LTT block, so learning truth table. At the end of the training, your weights here are fixed, okay? And typically, this is one computation. So you take your function and you apply it patch by patch. And each patch has size 3 by 3. If it's 3 by 3, that means 9. And if all the inputs are binary, we have in 2 power 9, we can compute the complete distribution of that function. So actually, this is what we are going to do. So you see, for all patches, we generate all the possible inputs and we collect all the possible outputs. Then, because it's a CNN 2D, we transform the square into a line, and we have the truth table over here. And at the end of the day, well, you have your truth table, you have your function in terms of DNF, CNF, INF, whatever you prefer, in terms of Boolean, actually in terms of a Boolean circuit. And I just want to highlight here something very important. Here, your weights are floating points, but here they completely disappear. You don't see it anymore. You don't need it. And actually, you can simply replace it by, here I replace it by the, I think it's DNF, but you can replace it by the truth table. It's exactly the same. And you do exactly the same computation as before. But instead of using the weights, this time you use the Boolean SAT equation. And if you want multiple filters, well, it's not complicated. You just stack them into layers, exactly like what you do for CNN filter. Okay, so I hope I was clear. Okay. So actually, this is exactly the same as the previous slide, but this time it's on 1D. It's a 1 dimension, whereas before it was 2 dimension. So yeah, it's exactly the same things. You can definitely replace this function here by the truth table. Okay. So rule design equivalent to a small exhaustive Boolean function. We have seen how to do it. The second point, I don't have the time to go into details. We can go back. I have slides for it, but we can go back if you have any question at the end of the talk. But now I want to see how we can design the overall neural networks. So here we have the smallest function, which is the filter CNN as a truth table. Now the question is how you integrate that into your overall neural network. Well, it's very easy. It's exactly like filters. So in one layer, you stack multiples learning truth table, and then you stack the truth table like this in parallel. Of course, you have the preprocessing at the beginning and the flatten plus the linear regression at the end. Okay, so we have seen how we can design a learning truth table. We have seen how to design a truth table. Yes. And now the question is, what are the performances of such a neural network? Well, if we have the size of each truth table to be 6, for MNIST, it's pretty easy to handle. For CIFAR10, between 6 and 25, well, actually, you have an accuracy between 70 to 87. And for n equals 16, you have 45% on ImageNet. ImageNet is considered as a pretty big image dataset classification task. Okay. So now that I presented the model, how you can integrate it with FHE. So here is how you can integrate TTnet into with Fully Homomorphic Encryption. So the setup is as follows. You have 3 main blocks. Again, the 3 main blocks as the beginning, at the first slides. So the first one is the preprocessing. which is here, N1. Then after that you do locally, and then you encrypt it. Okay, you send this encryption to the cloud, and here you use your truth table net in form of truth table. You flatten and you do a part of the linear regression in the cloud. And then you send it back, you decode your message, and you do the final computation. So this setup is a trade-off between accuracy and FHE running time, memory time performances. So we apply our model on two types of datasets. The first one is tabular datasets. So here we are in a free private type. So first line here, we have there is two main family, so CKKS and Torus FHE, and three main datasets, so adult, cancer, and diabetes. So what you can see is that, for example, CKKS don't handle very well tabular datasets. So they have a pretty low accuracy and pretty high time. TAPAS is also using Torus FHE. It's a work of 2018 by Oxford. And actually, they also have pretty good results, except on diabetes. Diabetes is a multi-class classification, whereas cancer and adult are binary class. So I think this is why they have such a high time here. But actually, what we can see is that TTnet, on the top of ZAMA for the homomorphic encryption toolbox, well, we are pretty fast and we have a pretty good accuracy. Now, if you know, ZAMA have also their own machine learning model that works pretty well. So if we want to compare ZAMA performances with ours, so in terms of accuracy, on the left you have ZAMA, and on the right you have TTnet with ZAMA technology. So we can say that they are pretty much equivalent, I would say. So for example, on 6-bit, they have a higher accuracy than us, but definitely the cost, I mean, the memory and the time is also higher. The rest, I would say that the 4-bit is equivalent to our big model. We are slightly faster, but they are slightly more accurate. So we can say that there are different trade-offs. And on 2 bits, the accuracy here are pretty low, but the memory print is also pretty low. Okay, so I would say that today, if you want to deploy your model, neural networks or XGBoost in production, I would say that right now it's almost ready to go. Just as a side, as a bonus, TTnet also offers global and exact interpretability. So it's another topic, but just keep in mind that we have this bonus also. So for image dataset, so this table is the same as the beginning, where we just add the two last line. We just add our performances. So first of all, the accuracy. Let's check the accuracy first. So we have 74.1%, which is exactly the same accuracy as Lola, and which is lower than ResNet, but a bit higher than Torus FHE with ZAMA technology in general. We can do it in 38 minutes, which is pretty good because it's the same time as the fastest one, which is ResNet. But more especially because we are very compact, we can have 0.8 gigabytes of RAM memory needed. And this is pretty nice for us because that means that our costs for 10K clients are pretty low. The same, so for two-stable net, if you can compromise on the accuracy and you can downscale to 62.2%, then it's even better. So you can downscale the memory to 0.08 gigabytes. But of course, you need to lose somewhere, like you need to lose in terms of accuracy. But this model here is pretty, I would say that it's pretty ready to production. And I say almost because, of course, CIFAR10 is definitely not such a big data set for image classification, but let's say that it's a good start. Okay, so I think we are almost done. Yeah, 40 minutes. So let's finish by the conclusion. So future works. We want also to integrate the preprocessing at the service provider side, not at the client side. We also plan to use TTnet in form of a Boolean circuit instead of using it in form of truth table. Then we have we want also to train truth table net with FHE, not only to infer with FHE, especially on tabular dataset. Like we don't target CIFAR10 so far. I think so far it's not really possible. But with tabular dataset, I have good hopes. Truth table net with homomorphic encryption with CKKS and open FHE, maybe we can try an implementation. And of course, the next big targets of ImageNet and natural language processing. Conclusion, take-home message. So I would say that the most important points are this one. This new neural network is based on truth table, lookup table. So by design, it can be integrated into Zama Concrete-Numpy technology. Fully homomorphic encryption and truth table net are ready to production for tabular datasets and almost ready to production for image datasets. TTnet is already relevant for multiple applications, so I didn't dive into that part, but we have some use cases on healthcare, we have some use cases on finance, we have a lot of different use cases right now. And in more general, we have positioned for PhD and postdoc. Also, we are open for partnership with industry, and TTnet is under NTO licensing. Okay, so thank you very much for your attention. Do you have any questions?
Thank you so much, Adrien. We're going to open it up to questions, starting with the questions in the chat queue. The first one was from Paul. So it says that you let the client, yeah, Paul, if you want to go ahead. It says if you want to, okay, go ahead, sorry.
No, I'm just trying to make sure that I understand here. So the approach is basically let the client do the first layer of sort of pre-processing and then still hide most of the AI logic server side. Is that the general idea?
So it depends on the use case. On tabular datasets, the preprocessing, everything is done in the cloud. There's two use cases. The first one is image, the second one is tabular dataset. Tabular dataset, everything in the cloud. Image dataset, yes, there is a preprocessing done at the user side.
Okay. So in that case, the user would be able to tell what sort of pre-processing you're doing to the data before it gets sent to the server, but they still don't know then how you combine that pre-processed data server side.
Yes.
So that's
yes. Sorry.
So I suppose with that, if you had some very novel type of pre-processing, then you're kind of giving away that secret to the client. So
you're right. You're perfectly right. In our experiments, we used a public layer, a public pre-processing. So I don't know if you know, but there are a lot of models open source right now for deep learning and for image classification. So what we did is we simply take one of them, which are public, and use it. So actually, the secret is kind of which preprocessing did we take from the public, all the public ones. But yeah, that's all. We didn't train specific preprocessing layer.
Does that answer your question, Paul?
Yeah, I think so. Thanks.
Okay. The next question was from Jack. Jack, did you want to take it?
Right. Can you hear me?
Yes.
Right. The timing, or whatever timing that you put there, does it include key transfer? Basically,
Yes, that's a pretty good question. No, it didn't. I think it didn't include the key transfers over the net. What do you mean by over the networks? You mean the time to send the keys from the user to the cloud provider?
well, you need to generate the key, right? Both the clients and the server need the key, right? You're using
Yes.
public private key, right?
So no, it's not included. It's not included, and generally in machine learning papers, they don't include the time. They only provide the time of inference.
Right. Okay. Okay.
So yes.
Yeah, I'm okay with the answer. Thank you. Thank you. Yes.
Okay, that was the last queued question. If anyone has a impromptu question now, I'll give it a few more seconds to raise the question.
I have a question. Can you hear me?
Yes.
All right. So I wanted to ask, what does this 38 minutes mean again? Does it mean one specific inference task basically for one specific inference? It takes 38 minutes, or what does it mean? This 38 minutes.
Sorry, can you repeat the question?
So in the table, you show that it takes 38 minutes. I didn't understand. It takes to do what? Like in this 38 minutes, is it one specific inference task, like from the client? It sends one image, and that it takes 38 minutes to return a label, or?
Yes, it's correct. So the time is the time includes the computation of the preprocessing, sending the data to the cloud preprocess the input, you send back the answer.
Okay, thank you.
Looks like we have another question from Sebastian. Do you want to start on voice?
Sure, I'm still getting familiar with all this, so bear with me if it's kind of a basic question, but I'm wondering about the cause of key rotation. Key rotation happened many times on the industry for many reasons. So what happened if we had to, as a client, I had to rotate my keys?
I'm very sorry, I don't know key rotation. I would love to answer your question, but yes, and my supervisor is, I think my supervisor is answering the question.
That's okay. Yeah, it might not. Yeah, it might be more general concept, so that's okay. Thank you, though.
I mean, I can explain what key rotation is. If you have, for example, your user table with all of actually this is the wrong example, but I'll keep with it anyway. If you have your user table with user passwords in there, they're going to be encrypted somehow, and this is a part where it's going to be wrong. Let's say that they're all encrypted using the same key, which horrible security example, but let's just go with it. If you have all of your user passwords encrypted with the same key, then you would want to change that key every year or so often. So substitute something other than user passwords, because that's, again, a horrible example, but some sort of user data encrypted with some sort of key, you'd want to change that, say, yearly. How does anything like that apply to this, I think, would be the question.
Yeah, I'm guessing in that case, most of the cost will be like in retraining, right, or reprocessing. But on the inference part, it should be pretty much the same cost.
Also, just a reminder to everyone, we'll be on the Discord after as well if there's any more complex questions that want to be asked in threads and text for clarity. Some questions take longer to answer as well. Okay, are there any more impromptu questions? All right. Well, I'm sure I speak for all of us here when I say that we really appreciate taking the time to present with us, Adrien. It was a pleasure to have you. And again, don't forget to join the community Discord if you haven't already at discord.fhe.org. And Adrien, if you're on there, if you don't mind to stick around and answer follow-up questions from anyone. And thank you everyone for participating today. And this meetup will be uploaded to FHE.org's resource page and YouTube within the week, so the whole community can benefit from it. And
Thank you.
Yeah, thank you. Suppose until next time, everyone have a good weekend.
Yes. Thank you. Thanks for letting me present. Thanks.
Thank you.
Have a good day.